So welcome my dear students. Last class we have discussed on the detailed analysis of the stress strain curve for a doubly reinforced section. So today we are going to discuss how to do the numericals for the design of a doubly reinforced section. So I'll just explain the design steps at first and then we will move on to the numerical part. So the design steps are: calculate the total bending moment, that is based on the load given. You need to calculate the total load, that is your dead load, live load acting on the beam. And if there is a concentrated load, you need to calculate the bending moment accordingly. That is, you will get the total bending moment as WL square by 8 due to your UDL plus WL by 4 if it is a concentrated load. Now the second step is to find the factored moment. Based on your type of loading condition, you need to find the factored moment. Factor of safety for the load should be applied and you need to find the factored moment. The next one is to calculate the MU limit for this section. Calculate the MU limit for a singly reinforced section. That is, you can calculate by MU limit is equal to QFCK square. Then you need to compare this MU with MU limit. When MU limit less than MU, which means the moment required for a balanced section is less than the applied or factored bending moment, then the section is to be designed as a doubly reinforced section. This we have discussed in the last class. You will need to divide this section into two, that is MU limit less than MU2. So first you will calculate the value required for MU limit, that is MU limit is equal to 0.87 FYAST limit into D minus 0.42 XU. From here you will get the value for AST limit. Now you need to find the value for MU2, that is the remaining moment, that is MU2 is equal to MU minus MU limit. From there you will get the value for, you can do the calculation for AST2, that is I can write AST2 in terms of steel as MU2 is equal to 0.87 FY AST2 into D minus D dash. Assume a certain value for D dash as 50 or 60 mm, you can assume that value, and based on that you will get the value for AST2. Now the calculation of ASC, that is the steel required under compression side, that is MU2 is equal to, you have again MU2 is equal to, in terms of compression steel I have FSC ASC into D minus D dash. Here you have two unknowns, that is FSC and ASC. Now first you need to find the value for FSC. In order to get the value for FSC, you need to find the strain at that level of steel. That is, to calculate FSC you require to calculate epsilon SC, that is epsilon SC. I will assume this as a limiting section because we have taken this as limiting section, and the remaining part is only two moment, that is the AST moment created by AST2 and ASC, which means the section there is no change in your XU, that is whatever AST2 is coming here, that much amount of ASC we are providing at the top also, which means XU, the section is now a balanced section. So you can calculate epsilon SC as XU limit minus D dash divided by XU limit into 0.0035. You will get the value for epsilon SC. Read the value of FSC from the table for the corresponding steel based on the epsilon SC value. From there you will get the value for ASC as MU2 divided by FSC into D minus D dash. Now you have obtained the value for AST limit, AST2 and ASC. That is, I can write the total tension reinforcement is equal to AST limit plus AST2 and total compression reinforcement is equal to ASC. So based on this you can draw the section diagram. So now you have understood the design steps. Now we will move on to the numericals, where you will understand more clear on how to do the design of a doubly reinforced section. So the question is design a rectangular beam of size 450 mm by 600 mm used for a effective span of 10 meter. The beam is subjected to a live load of 40 kN per meter. Use M30 grade concrete and Fe415 grade steel. Use limit state method. That is, you need to design a section having 450 mm and 660 mm total depth, used for an effective span of 10 meter. It is given the live load to be carried is 40 kN per meter. Given the concrete to be used is M30 grade and Fe415 steel to be used, and you have to design it by limit state method. So the given things are given, the width of the beam is given, total depth is given, span is given as 10 meter, the live load is given as 40 kilonewton per meter, M30 and 415 grade steel. So assuming an effective core of 50 mm, we will get D is equal to 660 minus 50, that is 610 mm. Now we need to calculate the load, that is here it is given live load, so we need to calculate the self load of the beam per meter length, that is dead load. I will get it as total depth 0.66 into width of the beam 0.45 into 25, that is the density of concrete. You get as 7.425 kilonewton per meter length of the beam. The live load is given as 40 kilonewton per meter, which means the total load is 47.425 kilonewton per meter. Now this load is subjected to a live load of 40, which means there is a load which is acting on the beam. Now in order for the design purpose, we need to find the factored load by applying the sufficient factor of safety, that is we will apply the factor of safety. Since it is live load and dead load, we need to apply the factor of safety of 1.5, that is 1.5 into 47.425, you will get as 71.1375 kilonewton per meter. That is the moment, ultimate moment weight or the design moment is WL square by 8, that you will get it as W is 71.135, L is 10 meter, divided by 8, you will get it as 889.21875 kilonewton meter, which means MU limit is equal to QFCK BD square, that is Q for 415 grade steel is 0.138, FCK is given as M30, that is 30 Newton per mm square, 30. B is given as 450 and D I will take it as 610, assuming 50 mm effective cover, which means I will get the MU limit as 493.22 kilonewton meter, which means from here you got the value for MU limit as what? 493.22 kilonewton meter, but your factored moment or design moment is what? 889.2185, which means MU limit is less than MU, which means you need to design this section as a doubly reinforced section. In the question it is given only what? Design a rectangular beam section. So you need to first identify what type of section it is. Then you need to go for designing whether it is a singly reinforced or doubly reinforced. So in the question it will be given only design a rectangular beam section. So which means first you need to identify whether the section is a singly reinforced or doubly reinforced. So here I can say that is MU is greater than MU limit, which means the section need to be designed as a doubly reinforced section. So design the section as a doubly reinforced section. So you need to calculate the value for MU2, that is MU2 is the additional moment to be resisted, that is MU minus MU limit. You'll get that value as 889.21875 minus 693.22, that is 195.996 kilonewton meter. Now the calculation of AST limit, that is you know now the value for MU limit and MU2. Now you are going to calculate how much value for AST limit, or what is the AST limit required. We have the equation for MU limit as in terms of steel as 0.87 FY AST limit into D minus 0.42 XU limit. So when you calculate that XU limit, you need to get the value, that is XU limit is equal to 0.48 times D, that is 292.8 mm. This is based on the grade of steel, you will get it as 292.8 mm. Substituting that value over here, and you know the value for Fy and D, and MU limit, you know the value as, the MU limit value as 693.22 kilonewton meter. You will get AST limit as 693.22 into 10 raised to 6 by 0.87 into 415 into D, that is 610 minus 0.42 into XU limit. XU limit is 292.8. You'll get this value as 3942.33 mm square. Now you obtain the value for AST limit. Now the next one is the calculation of AST2. Calculation of AST2. You need to assume an effective cover at the compression side. I will take it as 50 mm. That is D dash. I will take it as 50 mm. Now you have MU2 as 195.996 kilonewton meter. You need to write this in terms of MU2 in terms of reinforcement. That is MU2. I will get it as in terms of reinforcement. I will get it as 0.87 Fy AST2 into D minus D dash. Here the only unknown value is AST2, because you know the value for Fy, you know the value for MU2, you will get the value for D dash and D. So AST2 I can write it as 195.996 into 10 raised to 6, that is MU2 divided by 0.87 into 415, that is your grade of steel, into 610 minus D dash. You'll get as 969.37 mm square. So that is your AST2, the additional tension reinforcement to resist the moment Mu2. Now the next one is the calculation of ASC. In terms of for compression steel, I can write Mu2 is equal to FSC ASC into D minus D dash. So here you need to find the value for FSC. You need to get the value for FSC and ASC. So first you need to get the value for FSC. That is, to find the value for FSC, you need to find the corresponding strain value. To get the corresponding strain value, you need to get the value for epsilon SC. Epsilon SC I could write as x limit minus d dash by x limit into 0.0035. That is 1 minus d dash by x limit into 0.0035. This value you will get it as epsilon SC is equal to 1 minus d dash is 50. SC limit is 292.8 into 0.0035. That is, you will get this value as 0.00290 as epsilon C value. Now corresponding to this value, I need to find the value for my FSC. You have the value for your epsilon SC as 0.0029. That is, this is 0.002, 0.0021, 0.0022. From here you'll get this as epsilon SC value, that is 0.0029. This one is 0.0029. So we'll go in this way like this. We'll go towards the upper side. We'll go like this. Then it will meet your grade of steel, that is Fy design curve for your reinforcement, that is Fy divided by 1.15. that is this value. We'll get this, it will touch the curve over here. So when you are moving in this direction, you'll get the corresponding value for your FSC. That is, you'll get this here in this problem, you'll get this as 350 Newton per mm square. That is, if I explain once more, you have your epsilon SC value as epsilon SC as 0.0029. So that is, this value is 0.0029. So if I am going like this, it will touch my Fy over here. That is, in this direction I have moved. It will touch my Fy over here. Now this is your design curve. This is your design curve. Now when you touch your design curve, you need to move in the next direction. You need to move in the next direction, that is this one. So this value now will give you your FSC, that is this value of FSC, as I could write FSC is equal to 350 Newton per mm square. This is how you will find the value for corresponding stress in steel. That is, the FSC value will get it from the stress strain curve as 350 Newton per mm square. That is, Mu2 I could write as FSC ASC into D minus D dash. Now if I got the value for FSC, now the only remaining value here is ASC, that you will get it as 1000 mm square. That is, I could write AST is equal to, that is total tension steel is equal to AST limit that you have obtained corresponding the section as a balance section, and AST, that is the total tension steel, you get as AST limit plus AST2, that is 4911.7 mm square, and ASC you will get it as 1000 mm square. Checking for AST minimum. AST minimum is what? 0.85 BD divided by Fy. You'll get as 562.22 mm square, and AST maximum as 0.04 BD. You'll get it as 11,880 mm square, which means the AST required is okay. Now we will go for providing 8 bars of 25 mm Phi and 4 bars of 20 mm Phi at the tension side, and 4 bars of 20 mm Phi at the compression side. This actually, how to determine this will depend on a trial and error method. You can assume any number of bars which are available in the market that I have told you before. You can assume that it can provide this. Actually, the width of the beam is 450 mm. It is actually a very big section. That's why we got this much amount of reinforcement. So if I am drawing the section details, so you have the section like this with the overall depth as, we have a section with overall depth as 660, width as 450 mm. It's a very big section actually. I have obtained 8 numbers 25 and 4 numbers 20. So we will provide this in 2 layers, and we will keep a 25 mm bar as in between. This will provide 4 bars 25 in this layer and 2 numbers over here, and similarly 4 bars 25 at the top. 25 mm I'll denote it by red pen, and this 20 mm I'll denote it by green. 220, again 225, like this. Now I'll keep a 25 mm diameter bar like this. This is used to hold it. Again I'll place my 25 mm bar. Now 4 20 mm bars will be placed at the compression side. So this is how your section will look like. Now you have your total depth like this, 660, 450, and your bars will be placed in this way. The larger bar will be placed to hold these two bars, that is for a separation. Now you might have a doubt in while calculating the effective depth here. That is the first assumption, we have calculated the effective depth as 60 mm, 50 mm. Now the effective depth will change. We can either redesign, but generally we'll go for redesign this section. Again we'll find this. We will see whether it is okay. But in this case you just need to draw it like this and you can keep it safe like this. So I hope you are clear to design of a doubly reinforced section, and this is actually not the complete design of a section. Now here we need to provide the stirrups also. That is, after studying the shear reinforcement, we will provide the stirrups. We will check for deflection. Those things also we need to see, that we will discuss at the completion of your 3 modules. That is, we will discuss the complete design of a of a rectangular RC beam. So we will move to the next question. The next question is, at concrete beam 350 mm wide, 600 mm effective depth is subjected to a superimposed bending moment of 300 kN/meter. Design the beam section. Use M20 concrete and HOSD bars. Do it by yourself. If you got any doubt, you can ask me. So that's all for today's session. I hope you are clear with the design of a doubly reinforced section. So we will meet in the next class. Thank you and have a nice day.